I can't come up with, I've written down things in Dirac notation which are superfluous. You don't really know them how to, because the tensor has like parallel composition in space, like something, not necessarily in space, because this can be abstract space of course, and then sequential composition, they don't have a separate sort of position in the Dirac notation. If I write this, just if I write something innocent like this, are these two systems or is this a composition of two?
Yeah.
It's not clear in Dirac notation. So Dirac notation can't be formal actually. So okay, this is just how I calculate probabilities and this is the idea of computational basis, but it's like merely notation, no formal status. And as a consequence of this, it becomes a mess whenever, that's what I say, the tensor product comes into place. And many expressions become superfluous. So, but then everybody knows it's extremely successful, so there must be something about it. So what is mathematically about it that makes it so nice and easy? And so actually, the thing I'm going to talk about, S, what it does, it essentially formalizes Dirac notation and extends it in some way. So basically...
If I could just make a comment there, it was when I saw him using the standard ket and the standard bra that I suddenly realised that he was introducing an idempotent implicitly, which is what I talked about yesterday.
It's all implicit.
It's all implicit,
It's all implicitly. So, and it's good. So you want to understand what actually a lot of people say that these two things are like is a conjugate or something like that. So is it really?
I mean, I've always treated it as a tensor product. I've always treated it as a tensor product, although he doesn't in his book.
Yes, such. As a conjugate, but you could always think it's an edge. You could also think it's an adjoint. And the thing is, it's sort of both and neither. That's the funny part. It depends on which context you use it. So that's what makes it so messy. But I think we understand now what it is actually. So anyway, this is where Neumann was working. He thought like the most fundamental, and that's what people like Perot and everybody who came after thought, that like the essence of quantum mechanics has to be searched for here, and they had this idea with you interact with the system and you retrieve data, and the way you interact with the system determines the structure of quantum mechanics. That's sort of all the answers. So that's what I'm going to do here. I'm just going to forget for a long time about the whole concept of measurement. And I'm going to just think about one thing, like you have got more than one system. So there's just this idea that you have the physical ability to conceive two things as one. Does this impose any kind of structure on your experience of physical reality just at an operational level? This looks very minimal, this looks very basic, but the thing is I'm going to show that actually by doing that, this comes out. That actually compound is more basic than the idea of interacting with the system or measuring the system. That's like the philosophical setting I start from. And something else which is going to be implicit in my setting is the concept of process in some way or another. Okay, so the main mathematical result is actually that quantum theory can be completely reactionized in terms of tensor product only, compounds only, at some abstract level then. And the mathematical context will be categorical semantics. So the way we start is with an operational foundation, and then there are these two things which we introduce, and I think they're really essential to everything we do. One of them is types reflecting kinds. Types is again a computer sciencey concept. What does it mean? It's so obvious that, and it's so weird that it never occurred in science before, I find. Like types means the following. So you're working in the lab, you've got your quantum system, you're measuring it. So I give a name to the kind of system which I have. It can be a field, it can be, say a spin system, and I call it A. Like a field would have a different name than a spin system, for example, because it's clearly has it's a different mathematical description. And then I measure it, and what do I get? I get a measurement outcome, which is classical data. For example, it means a location in space, which is a classical data. It's an element of the real line, say, and I'm going to call that X, together with the collapsed state. So, and this is what I call a type. I've got something which goes from quantum system to a pair of quantum system and classical system. This is what I call type. And these two things are not equal.
Sorry, they what?
They are not equal.
Not
A is
equal.
not equal to,
Sorry, I just didn't catch
to
the
the
word.
pair
Not
of x and a. I'm just using the tensor product here. Just ignore about the semantics which I give to the tensor product, but this is the way it's going to be done. So, but it's clear that this is not equal to that. Now, if you look to standard quantum mechanics, you've got a unitary operator. What is the type? H to H. You've got a density operator. What is the type? H to H. You've got a measurement, self-adjoint operator. What is the type? H to H. You can compose all these things in the Hilbert space formalism. They all admit the same H to H behavior, but they don't mean that. The only one who really means H to H is you, unitaries. A measurement is not H to H. A measurement gives you classical data. Where is classical data in the H? A density operator, it's not even a process, it's like an element, a state. So it shouldn't be H to H. It shouldn't be. But they all admit, so types really means that you look at the thing and you know what it is about. And this, for example, says I'm classical. This says I'm quantum. This says I'm a process from quantum to classical and quantum. I'm a measurement. And you can't just compose two measurements. What you can compose is a measurement together with, say, an identity on X. So which means I preserve my first set of data. It's so natural once you start thinking about it, that's how things should be. But you don't do that in physics. So that's the concept of type. And as I illustrated, like quantum mechanics, there are no types. Now, compositionality is just the same thing. It's like what I was saying, that if you do one measure, if you get the notion of composition in your theory, and you do one measurement, and then you do another measurement, then you want this combination of these two processes to be represented by the composition, mathematical. You want to give semantics to the concept of composition, like first doing something, then doing something else. This is of course not the case in quantum mechanics, because if I take a self-adjoint operator and I compose it with another self-adjoint operator, it means nothing. Yes?
So I just want to be clear about something. When you've written this A goes to X times A,
Yeah.
I mean the X is something definite, is it? It's a definite value. Because I'm just trying to think, Schrödinger doesn't give you a definite measurement outcome. But X is something definite, is it? Some definite point on the real.
It would be the number in your spectrum. It would be the value of the diagonal of.
I'm just trying to work out whether you're adding something to Schrödinger dynamics by writing that or not.
At this stage, there is nothing like Schrödinger dynamics in the game yet.
But X is something definite. It's
a value, yes.
It's a definite value. It's not
value.
a probability distribution.
It's say it's like your picture of your bubble chamber. You've got this picture, you can put it in drawer, and a year later you can look to your experimental data still.
So it's something definite.
It's something definite.
It's beyond Schrödinger. I mean,
yes,
you shouldn't compare it, but in the spirit you're asking the question, it's beyond Schrödinger.
Right.
You know, there is something very weird.
There
is something very weird about the quantum mechanical formalism. People are always talking about measurement problem, and measurement problem is about